Sri Sai Ram. Welcome to the fifth session of this chapter, Motion in a Straight Line. In the last class, we have studied about the differentiation, right? It is a part of calculus. And today we are yet again back with the calculus, but with another one more interesting topic, which is integration. What does the name integration suggests? It suggests the adding up or summing up. So in short, it is just the adding up, and we dig deeper into this topic and decipher what are the concepts lies behind it. All right, integration. Let us go into the informal definition of the integration. What is it? Integration is an inverse process of differentiation. So what do you mean by inverse process of differentiation? We have studied differentiation in the last class. What do you mean by inverse process of differentiation? It means it is a process of finding the function whose derivative is given. Okay, that means what have we done in the earlier classes? We have been given a function, right? And then we are asked to find how the slope of that function is changing, right? So how the slope of the function is changing with respect to x, that we call as a derivative of the original function. So what do you mean by inverse process of differentiation? That means here we were given the derivative function. So originally differentiation. So what do you mean by differentiation? So differentiation is going from original function to derivative function. Derivative function. Now here what we are doing, it is inverse process of differentiation. That means we are given this. So integration is nothing but where you are given a derivative function. Then we need to go back to the original function. We need to trace back to the original function. So this is what the integration is about informally. All right. Now let us see the actual definition. Suppose f of x is a derivative function of g of x. So original function is your g of x. All right. Now what is f of x? F of x is the derivative of g of x. All right. So how you can write this? You can write this as d by dx of g of x is equal to f of x. So derivative of g of x gives you the f of x. This is up to the differentiation, right? Now in this class you will be given f of x. You need to trace back what the g of x is. So that is what it is given. Now if you are given the derivative f of x, this is the derivative function f of x, and we have to find the g of x. Previously in differentiation, g of x is given, d by dx of g of x, you are obtaining f of x. Now you are given f of x, you need to go back to g of x. Then this can be done with the help of integral calculus. How can we get g of x from f of x? By using integral calculus. So this is the main motto of this integration. Now let us go further and see what is the process, how we can get back to here. All right. Okay. So the process of finding the function whose derivative is given as is called as integration. So tracing back the original function. So now let us get to the more formal definition. If f and g are functions of x, all right, such that g dash of x is equal to f of x. What is g dash of x? It is nothing but d by dx of g of x. So it can also be written as like this, g dash of x. G dash of x is d by dx of g of x. So g dash of x is f of x. What is derivative here? F of x is a derivative of which function? G of x. Alright. Then the function g is called as the antiderivative. Okay. So f of x is called as a derivative of g of x. By differentiating only you are getting f of x. Now what the g of x is called from the f of x perspective? It is the antiderivative of f of x. Alright. Or it is the original function, right? That is the reason we are also calling as primitive function. Because f of x is, because g of x we are having, on differentiating that we are getting f of x. Alright, where the f of x came from? What is the original mode of integration? We are getting back to the original function. So this f of x, this g of x is also called as primitive function because it is the original function from where the f of x is obtained in the first place. Then we are tracing back to the original function. So primitive function of f of x is called as g of x, or in simple terms we can also call as it is a simple integral of f with respect to x. So g of x is nothing but integral of f of x, and how you write it? It can be written symbolically as integral of f of x dx. Alright, here f of x is your derivative function. When you integrate it with dx over dx, what happens? You are getting back to your original function. Okay, not only that, you need to have some constant. Alright, why it is necessary we will discuss in the next slide. Alright, so d by dx of g of x is equal to f of x. If this is the condition, then you will get g of x as integral over f of x. This is called integral over f of x. Okay, and the function g of x whose integral is f of x is called as what? Integrand. So this f of x we call as an integrand. Alright. So up to here I hope everything is clear. Now let us go to the next thing. So fundamental formula of integration. So using that basic definition, you can easily find the integrals of so many functions. But point to be noted is you can differentiate many functions, but integration we cannot do for each and every function. Alright, this you need to know, and this will be further clarified in your maths class. So we will be discussing here which is only constrained in the physics. Now fundamental integration formula, using that integral f of x dx equal to g of x, using that we have some formulae. Alright, so before going to that, let me clarify why we are taking that constant plus c. Integral of f of x is dx equal to g of x, but it does not stop there, right? We are adding plus c. In the previous slide we have shown you. So let us see. Since d by dx of g of x equal to f of x, now integral of f of x dx equal to g of x. You are tracing back to the original function. Original function is this, derivative function is this. Now you integrate the derivative function, you will get the original function plus c. Why this c is? Okay. So let me take an example. y1 is equal to, y is some function of x. It is varying as x square. Okay. Now let me write what is dy1 by dx. It is nothing but what? 2x, right? Now one more function let us take, x square minus 1. Okay. Now differentiate this function also, dy2 by dx. So what does this derivative gives you? This function's derivative gives you, this also gives you 2x. Now for suppose if I integrate both of this, I should get back to this. But both the derivative functions are equal. But my original function is different, x square minus 1. By integrating this, I cannot get back to x square minus 1. Right? So what is the problem here? It's not the problem. What is happening here? You need to understand derivative function will only give you the how the slope is changing. It does not tell you where it is cutting the y-axis. See here, what is the graph? If I plot the graph of this, what it will be? It will be simply like this, parabola. Okay, if I draw this graph, how it will, what it will be? It will be like this, and this is your minus 1. This is x-axis, that is y-axis. So both the shapes are same. This derivative function will give you only the shape, how the slope is changing. It does not give any information about where it is cutting the y-axis. Alright. So that is the reason to adjust according to your boundary conditions. In your definite integral, you will have the boundary conditions. There you don't need this c. But here in indefinite integral, you need to add c, because you don't know what the original function is. Okay, by which constant you need to add, you don't know that. That's why you need to add plus c there. Okay, I hope everything is clear. So therefore, based on the above definition and various standard differentiation formulae, we obtain the following integration. So there is a list of integration formulae which you need to conceptualize in your maths class, but as far as now, you need to, I can't say by heart, you need to just go through it, keep on practicing so that it gets into your mind. Okay, now let us go what the formulae are. So first one, you already know, d by dx of x power n by n plus 1 is equal to x power n. So let me solve this. So what is x power d by dx of x power n plus 1 by n plus 1. So when you differentiate, it comes n plus 1 into x power n plus 1 minus 1 by what is there, n plus 1. So this gets cancelled, this gets cancelled. So what is remaining? X power n. Okay, can here n be equal to minus 1? N cannot be equal to minus 1, because anything by 0 is undefined in mathematics. So when n is not equal to 1, apart from everything, d by dx of x power n plus 1 by n plus 1 gives you x power n. Alright. So if this is your what, g of x, this is your f of x. So integral of this should give you this, right? Integral of x power n dx over dx gives you this plus c. Okay. Now the second function, integral of log x, you already know. Integral of log x, you already know 1 by x, right? Now the integral of 1 by x dx should give you what? Log mod x plus c. And here these conditions you need to understand. So log 0 is not defined, right? So x should not be equal to 0. Third one, d by dx of e power x, you already know, that is e power x. So integral of e power x should be again e power x plus c. Fourth one, d by dx of a power x by natural log of a is equal to a power x, where a is greater than 0. Why is a greater than 0? Log 1 is not defined and log 1 is 0, and log a should be greater than, because log cannot take the negative values, right? So here a should be greater than 0 and a should not be equal to minus 1. So how this came? You already know that d by dx of a power x is equal to what? D by dx of a power x is equal to what? A power x natural log of a. Here what we have done? We have done this, we have put it here. So it becomes by here. When it comes here, what we divide both sides by natural log of a. So what becomes on the right side? It is remained with a power x. So our aim is to make a power x on the one side so that we can take the integral of a power x. Alright. So integral of a power x dx will give you a power x by natural log of a plus c. So these are the formulae. Fifth one, d by dx of cos x is what? Minus sin x, right? So d by dx of minus cos x is your sin x. Our aim is to integrate sin x. That's why we are taking positive sin x on the right side, remaining everything we are shifting to the left. So what should be the integral now? Integral of sin x is minus cos x plus c. Similarly, what is the d by dx of sin x? Derivative of sin x is cos x. So integral of cos x should be sin x plus c. So d by dx of cos x is minus sin x, right? So integral of sin x is minus cos x. It is just the opposite, the signs. Now, so d by dx of tan x you already know is secant square x. So integral of secant square x should be tan x plus c. Integral of minus d by dx of minus cot x is cosecant square x, and so the integral of cosecant square x will be equal to minus cot x plus c. D by dx of secant x gives you secant x tan x, and integral of secant x tan x will give you secant x plus c. Similarly, d by dx of minus cosecant x is equal to cosecant x cot x. Integral of cosecant x cot x is equal to minus cosecant x plus c. These are the standard formulae which will be useful either in your mathematics and during your physics as well. Now, let us see this one. This is interesting. So let us solve this. D by dx of log sin x is equal to cot x. How it can be? We have not talked about this in the earlier classes. So here we already know that d by dx of log x is 1 by x. If there is a x here, we can easily able to write as it is 1 by x. But instead of x, it is sin x here. So how we can do here? There is a small trick. So procedure we can tell. D by dx of log sin x, right? So how we can do this? First, just imagine that it is x. Sin x is x. So if it is x, how can you write 1 by x, right? That is equal to, instead of x, what is there? Sin x is there. So it is 1 by sin x. Now after doing this, you need to again differentiate this sin x, which is instead of x, what is there? Sin x. This you need to again differentiate. D by dx of sin x. What is that? 1 by sin x into, what is d by dx of sin x? It is nothing but cos x. So cos x by sin x will give you cot x. Okay. So what we have done? We have done just exactly how we do with x. Instead of x, what is there? You do that. So it should be 1 by x. Instead of x, what is there here? Sin x is there. Put sin x, and again differentiate d by d, differentiate this value. Okay. One more example you can see. So you already know that d by dx of log sin x is cot x. So integral of cot x will be equal to log sin x plus c, log mod sin x plus c. Similarly, just do for d by dx of minus of log mod cos x is equal to tan x. Just derive it. Pause the video here and derive it. I hope you have already tried it. Let me tell you. So just think this. if there is x, we would be writing 1 by x, right? Because there is no x, now we have to write it as 1 by cos x. So first step, so it is minus 1 by cos x. So what is the second step? You need to differentiate what is there in this place of x. What is there in this place of x? Cos x. So it will be d by dx of cos x. What is d by dx of cos x? Minus sin x, right? So it is minus sin x by cos x. Minus into minus plus sin x by cos x is equal to tan x. So that is what it is. So integral of tan x will become minus of log of mod cos x plus c. So similarly, d by dx of log mod secant x plus tan x is equal to secant x. Therefore, integral of secant x dx will give you log mod secant x plus tan x plus c. Similarly, d by dx of log of cosecant x minus cot x equal to cosecant x. Therefore, integral of cosecant x dx will give you log of cosecant x minus cot x plus c. I hope you understood this. You can also write as d by dx of minus of log cosecant x plus cot x is equal to cosecant x. Then integral of cosecant x will give you minus of log cosecant x plus cot x plus c. Okay, so that also you can try out as a home assignment. Now let us go to the inverse functions. D by dx of sine inverse x by a will give you 1 by square root of a square minus b square. In the previous session we have studied sine inverse of x is equal to 1 by square root of 1 minus x square. Instead of 1 we have a here, so that will be 1 by square root of a square minus x square. So what this integral will be? Integral of dx by a square root of a square minus x square will give you sine inverse of x by a plus c. So d by dx of cos inverse x by a is equal to minus 1 by square root of a square minus x square. Similarly, therefore, integral of minus 1 by square root of a square minus x square dx will give you this. So these are the formulae which you can see and you can simulate. Okay, if you have this, if you remember this, you can able to remember these two. So this kind of relations you need to understand when you see, when you solve or by heart the integration. Okay, otherwise it is very hard to memorize all this. So d by dx of 1 by a tan inverse x by a is equal to 1 by a square plus x square, and previously it was tan inverse x. Now it is what? Tan inverse x by a, 1 by a tan inverse x by a. Now therefore integral of dx by a square plus x square is equal to the original function. This is the original function. Get back to the original function, 1 by a tan inverse x by a plus c. So these are the whole lot of what integrals where you can memorize and you apply when you solve the problems. All right. So as we have gone through this formulae, can we just solve some of the examples? Okay, let us solve some examples. So these are the examples. Solve, these are the 4 examples. First one is integral of x dx, second one integral of 5 into e power x dx, third one integral of 1 by 2 root x dx, fourth one is integral of 7 power x dx. Pause the video and solve it. Okay, so let me solve. What is integral of x power x into dx? So it is in the form of what? It is in the form of x power n, right? X power n plus 1 by n plus 1, where n is equal to what here? N is equal to 1, right? N is equal to 1. So which implies 1 plus 1 by 1 plus 1, that is equal to x square by 2 plus c. I hope you got this answer. What is the second one? Second one, see, 5 is a constant. Is it changing with x? I mean, it is a product of this some function. So whatever the function is changing, if you multiply it by 5 times, you will get the answer. So this 5 has no effect on integral. The integration has an effect on e power x. Alright. So you can take the 5 outside, e power x into dx. Now, what is the integral of e power x into dx? It is nothing but e power x only. So it is 5 into e power x plus c. Okay. This is the second question. I hope this also you got the answer. Now let us come to third one. It is 1 by 2 root x. This 1 by 2 is multiplying, the constant is multiplying to a function. You can take out the constant outside. So 1 by 2 square root of, how can I write root x? I can write root x as x power minus 1 by 2 into dx. Right. So what is the n now here? N is minus 1 by 2 here. So what you can do here, according to the formula, x power minus 1 by 2 plus 1 by minus 1 by 2 plus 1. Right. So what is there? Into the whole into 1 by 2. Okay. What is minus 1 by 2 plus 1? 1 by 2. What is 1 by 2 plus 1? 1 by 2. Here this comes out to be 1 by 2. Here 1 by 2, here 1 by 2 cancel. What is remaining? That is equal to x power 1 by 2 plus c. That is equal to square root of x plus c. This is the integral of this function. Okay. I hope everything is clear. Now what is integral of 7 power x? What is integral of a power x? Integral of a power x dx equal to a power x by natural log of a. So what is a value here? A is 7. So this is equal to 7 by natural log of 7 plus c. I hope everyone is clear with these examples. Alright. So these are the simple integrals. Now you may be asked, or you may come across some functions, different functions. You may come across different functions where each one is product of, where the integral is product of two functions, where the integral is summation of two functions. Here we have one function, x is one function, e power x is one function, this is one function, 7 power x is one function. There may be several functions inside the integral. So how we will solve that? Let us see that. Okay. Now if u, v, z are functions of x. Okay. So if we are asked you that u plus v plus z dx. So here there are three different functions. Okay. There is a whole summation of functions over dx. So how we will solve this? We know only single functions, right? integral of ux, u into dx we can solve, integral of v into dx we can solve, integral of z into dx individually we can solve. But if it is given as summation of functions, what is the formula? It is nothing but summation of integrals of individual functions v dx plus z dx. So this is the whole summation function. It is the individual function. Integrate with each function first and then you can add up. Alright, if there is minus or plus, anything you can add up, anything you can do in between. Alright, this is the formula for this is the algebra of the function, algebra of the integration. Now we know this, or for example you can take it as, we can take an example as integral of x plus sin x dx. So what we can do? We can do as integral of x dx plus integral of sin x dx. Alright. So what it will be? X square by 2 we have already studied, plus what is integral of sin x? Integral of sin x is minus cos x, right? So, minus cos x plus c. So both constants you add up together, you will get c. So this is the integral of x plus sin x. Alright. Now you are adding or subtracting a function. You can use this. If I write here as, instead of x we can write minus, if the integral is minus here, so what I can do? Instead of x you will do minus here. Okay, it is as simple as that. Now if you are asked integral of u into v dx, what is it? Addition and subtraction of two functions is okay, but here there is a product of two functions. For that we have a formula. I have formula of uv dx is equal to u first function into second function, integral of second function dx. If this is your first function, this is your second function. First function into integral of second function dx minus integral of differential of the first function, derivative of the first function, again integral of into integral of second function. Okay, the whole integral you have a dx. See, u into v, this is your first function, this is your second function, into dx. So how do you integrate? First function into second integral of second function dx minus integral of derivative of the first function into the same thing here, the same thing you write here, integral of v dx, because it is having an integral, so you need to write a dx over dx. Okay, this is the thing. Now you may ask, sir, you are telling this is the first function, this is the second function, how do you know this is first function, this is second function? Yes, there is a rule called as a eilate. There is a rule called as eilate. If the functions are the combinations of these functions, u will be taken in this priority order. Okay, okay. Let us see what they stand for. E stands for inverse functions. L stands for logarithmic functions. A stands for algebraic functions. T stands for trigonometric functions. E stands for exponential functions. if the integral is the combination of, for example, logarithmic and algebraic. If one function is logarithmic, one function is algebraic. Okay, logarithmic means you have studied log of x. If one function is logarithmic and one function is algebraic, for example, it is as root x or 5x, something like that. So which function will be your u? What is coming first here? Logarithmic is coming first here. So you in the preference order, you will take u as the logarithmic function. If you have the functions which are combinations of inverse and exponential, which comes first? Inverse comes first. So you will take u as the inverse function. If you are getting the combination of algebraic and trigonometric, which function you will take? Yes, basically you will take u as the what? Algebraic function, because here algebraic comes first, then you can take trigonometric. Alright, so fix one u and the rest is your v when there are two functions. Alright, so this is the algebra of the functions when you have the integral over the product of two functions. Okay, let us solve an example on this. For example, if I give you integral of x sin x sin x dx. So what is your u here? So this x is what? X is algebraic and this is trigonometric. In isolate, which is coming first? A is coming first. So this will be your u, this will be your v, the rest is your v. So this is your u, this is your v. So according to your formula, use this x into what? Integral of sin x dx minus integral of d by dx of x, integral of again the same thing sin x dx, for overall it is dx. So what is here? X. What is the integral of sin x? It is minus cos x. So it is minus cos x minus what is d by dx of x? It is nothing but what? 1. So it is 1 into what? What is integral of sin x dx? You already know it is minus cos x dx. Okay, minus cos x dx. So minus into minus will become what? Plus. So it will be minus x cos x plus integral of cos x dx. So it will be minus x cos x. What is here integral of cos x? Cos x integral is nothing but sin x plus sin x dx. Understood? This is your integral. So let us solve one more integral. Integral of x into e power x. So this becomes u, this becomes v. So according to the formula, what? X into integral of e power x dx minus integral of d by dx of e power x. The same thing you write here again, e power x dx whole over dx. Now we already know integral of e power x is e power x minus d by dx of x is 1. Integral of e power x dx is e power x again into dx. So this becomes minus e power x plus c. So this is your integral of this. Understood? So these are the some of the examples where you can solve the algebra of the integrals. All right. So I hope you are well accustomed with the integrations, how you solve the integrations when you have to multiple functions, how you will solve if it is addition. If you are given the summation of the function, you will take out the each function and integrate, and you can sum it up. If you are given the product of the functions, it is how, using the formula and using the preferential order of the I-late rule, you can take u and v and plug into the formula which is given to you. So this is how you find out the integration. There are several other methods also, integration by substitution. So integration is a vast topic where in your 12th class you will be learn, it is spread over 3 to 4 chapters. Okay, so these are the basic things these are the basic things in which we can take out some tools and use it in physics. Okay, now let us get back to physics. Where do we apply this in physics? So where do we apply this in physics? Right, let us see. So calculus is deeply integrated in every branch of physical sciences. So in physical sciences you can see the force is varying over distance. Okay, so and the acceleration is varying. So everything is not constant, it is varying with the distance or with the time. So how will you trace back any function which is changing so rigorously, so continuously? So you need calculus for those kind of problems. If it is discrete, what you can do, you can take out the slope, or you can take out the area between that and multiply and get the result. But when it is not discrete, when it is not, if the, for example, what is acceleration? It is the derivative of velocity, right? Now if you want the velocity from the acceleration, you need to integrate acceleration. If you know acceleration is not uniform for some period of time, for each and every second the acceleration is changing. Okay, how you can find out the velocity from acceleration? For small time intervals, you need to find out the acceleration and add up. That is very Hercules task, right? So what you will do? That's why calculus is very important in that. See the function of how the acceleration is changing over time and integrate it. You will just come up with the velocity. So that's how the calculus is very much deeply involved in the physics, in the physical world. In the physical world, what you will see, you will not see anything that absolutely it is constant. You will see, you will come across so much of variables where it is changing very rapidly over a small interval of time where you cannot trace it. So if you find out that function of how it is varying and plug in the integration, and integration, I mean plug in the calculus way. If you want integration, you want differentiation, you can do any sort of thing by using this calculus. So this is a tremendous discovery by Newton. Tremendous invention by Newton. So integral calculus covers the accumulation of quantities such as areas under the curve. So when we started this class, we came from the definition of that integration is the inverse process of difference. Geometrically, what we are doing? We are doing integral of f of x into dx, right? This is one quantity, this is one quantity. What is this f of x? You put in some x value, you get f of x according to the function. So f of x is your y coordinate, right? So if there is a y axis, this is x axis, you are putting x value, you are getting corresponding f of x value. That is one. And what is this dx? Dx is the slightest increment of x, how the function is changing in that slightest increment. So dx is very small. So this is the width and this is the length. So when you multiply length into width, what does it give you? It gives you the area. area of the rectangle, right? So there are so many of f of x under the curve. There are so many f of x inside the function, right? F of x is the overall function. If you are putting many values of x, you will get so many corresponding values of f of x1, f of x2, f of x3, f of x4, so many lengths into the increment of x. You will get the area under the curve. Geometrically, what you are doing is f of x, integration of f of x over dx is giving you the area under the curve above the positive x axis. Alright, let us explore it further. So although we do have standard methods to calculate the area of some shapes, calculus allows us to do much more. Standard shapes, you mean circle, what is the area of circle? Pi r square, sphere 4 pi r square, triangle half base into height. But these are some regular shapes. What if you come across some irregular shape like this? This is not a triangle, not a circle. So how do you calculate the area of this kind? In your future classes, you will come across this curve. This curve we mainly called as a Gaussian curve. So how we can find out the area of this? Just now we have discussed, we can calculate the area by the method of integration. To find out the area on the shape like this, it would be very difficult if the calculus wasn't there. So let us see, let us find how we will find the areas. So the area under the curve. A building has a parabolic archways. You can see the large arches rise, you have the parabolic archways like this. So our question is, how much glass is needed? We need to fix the glass here. How much glass is needed to fix here? In order to find that, you need to know how much area it occupies. Yes or no? Then only we can fix the glass. So in order to fix the glass, our first aim is to find out the area. So in how many ways can we find out the area? We can find the area in two ways. How? Using the approximation, finding the areas of triangle, that is the first method. Second is integration. So let us go and see what is this finding the areas of rectangles method. See, before integration was developed, only approximation to the answer by dividing the space into the rectangles and adding the areas of those rectangles. So before, what we could only do is, if you want to find out the area of irregular shape, what we can at most do is divide that shape into equal rectangles, small rectangles, and add each of the area of the rectangle which is inside the arch. Then we can get some number that will be your closest approximation to that area. So what is this? See, this is the arch, right? Now we divided this arch into several rectangles, equal rectangles of equal width. Okay, this widths are equal. So we have divided this arch into several rectangles, and what we did, we added up all the areas to get the areas closest to approximation of this area of the arch. But the thing here is, we are neglecting these areas, right? This is not the actual solution. This is the closest approximation to the area, right? Now, if this is your x-axis, this is your y-axis. If you put an x here, this will be your f of this is, if this is x1, this is x2, like this, you will have so many x's. So for this corresponding x1, you will have f of x1. This is length of this triangle. Similarly, f of c, you have similarly at x equal to c, you will have f of c corresponding y value. Okay. So this is your f of c, and this is your increment in x, how the function is changing, right? How the slope is changing of the arc. Okay, at this value the slope is this. So it can be thought it is uniform over dx distance. So this distance is what we call as dx distance. Over this value, I can approximate that the slope f of c is uniform. Alright, so there are so many things here. F of x1, this is f of x2, f of x3, so many lengths are there. You multiply all those lengths into the dx, this is the width, every width is the same. So you will get close to the area of the path. So what we can write as summation of f of xn dx, where n is running from 1 to n equal to n. So if there are n rectangles, this rectangle is starting from 1 to it is n. So every rectangle, this is the area of the rectangles. Correspondingly the length is changing. As the x is changing, correspondingly the length is changing according to the function how this parabolic archway is changing its slope. Now how can you get the more and more approximation, more and more closer value to the actual value of the parabolic arch? If you divide this arch into more and more rectangles of equal halves, equal parts, right? This distance, this is delta x, if this is delta x, if delta x is close to 0, tends to 0, then what happens? You will get more and more good answer, more good answer that is equal to the area of this arch. That is what actually the integration is. This width which dx is tending to 0, so that you know how the slope is changing. You know at each point how the slope is changing. You just add up, you just product them, f of x into x, f of x into x, f of x into x. F of x is nothing but how the slope is changing at each and every point. That is a derivative function, right? Derivative function is nothing but how the slope is changing. So you will know that how the slope is changing at each and every point. You multiply with that point, then you will get what? Original function. Original function is nothing. Geometrically it gives you the area, because length into breadth, length into breadth. So small rectangles you are adding up to form this area, right? So the height of each rectangle is found by calculating the function values as shown for the typical case x equal to c. So for x equal to c, you already know that for the function it is f of c. If this is the function, if these are the x values, this is the function, how the function is changing with respect to x. At x equal to c, you can see this is the height. So there are many x values, you can take many x's. So we get a better result if you take more and more rectangles. This is what we have discussed. So finding the areas using definite integration. So up to now we have discussed about indefinite integration. What do you mean by definite integration? Definite integration is nothing but I want the area of the curve, under the curve, from this point to this point. I am very definite about it. So I have some lower limit, I have some upper limit of the function. Within this limit, I need to find out the area under this curve. Okay, that we call as a definite integration. Okay, so there must be a better way than finding the areas of triangles, right? That's why we call integration as problem of areas, right? We are having the problem of area in finding the irregular bodies, areas of irregular bodies. Now, in differentiation, what is the problem? That was the problem of tangents, because at each and every point the slope is changing. We want a function of slope where we can plug the x value and find out at yes, at this point the slope is this. So that is the problem of tangents. Okay, we cannot draw the tangent at each and every point and find out the slope. We need to have the derivative function there. Here in the same way, we need to know we need to have the integration of that function. We cannot simply add up the rectangles. There are so many variables. Okay, some functions may vary with x differently. Some functions may vary very drastically. It may increase suddenly, it may decrease suddenly. So how can you find out the areas? The approximation can only give you can only take you to some distance. If you want more and more accuracy and precision, you need to employ the calculus. All right. So what was developed? Integration was developed by the calculus was developed by Newton and Leibniz to save all the adding areas of rectangles work. All right. So in general case, see, this is the function y equal to f of x, how it is changing. But our area of interest is we need to find the area between these two. Between these two. So you need to also note that the function is above the positive x-axis. It is, the curve is completely above the positive x-axis. Now, in general, the exact area under a curve y equal to f of x from some point A, which we have seen from point A to point B, right? Our area of interest is this. The curve is here, the curve is also here, the curve is also here, but we are not bothered about it. We are only bothered from here to here. So this we call as a lower limit, this we call as, this is lower limit, this we call as higher limit. Okay. Now from y equal to f of x, from x equal to a, which is lower limit, to x equal to b, that is higher limit, up to this much only I can go, is given by the definite integral. So area is given by integral. So below this sign, integral sign, this is your lower limit. From a, it is going to b, this is your higher limit. Okay, this is your lower limit, this is your higher limit. If integral of f of x dx is your capital F of x, okay, how you will evaluate this expression? If f of x, capital F of x is the integral of f of x, that means integral of f of x dx is capital F of x. Okay, then the area is given by, see, this integral is equal to this. This is up to indefinite integration. Now you need to put the limits. This is your higher limit, this is your lower limit. Now what you do is, after the integration, you need to just substitute the limits. Okay, up to where? From x equal to a to x equal to b. X equal to b is your higher limit. So when you get this function, plug in the higher limit value here, f of b, you will get some value, minus f of a. A is the lower limit. Instead of x, where all the x is there, you put this value of a. Where all the x value is there, you put the value of b. You subtract them. This is your what? Definite integral from a to b. This is your area under the curve from a to b, where b is your upper limit and a is your lower limit. That means from a to b, you are calculating the area under the curve f of x. Okay, this is the thing. So area under the curve is useful in finding the acceleration, velocity in kinematics. How? See, geometrically integration of function gives the area under the curve, right? So if the acceleration is given to you, if the slope is given, how the function is varying with time is given to you, what you can do? You can integrate the acceleration over the time to get the velocity. Yes or no? So a is dv by dt. A is dv by dt. So a is the derivative function of velocity with respect to time. Now you want the what? Original function v. So how we can do? you have to integrate what? Acceleration. So that is what is given here. See, V is integral of A dt because A is dV by dt. Displacement is integral of V dt. So integral of V dt, you already know what is V here. This is this. So instead of V, you write this integral of A dt. So it is double integral. So first integral you will get velocity, and then you integrate velocity, you will get displacement. Alright. So this is a plot of varying force in x direction as shown in the figure. See, this is the force, this is the displacement. As the displacement is changing, the force is also changing, right? Using our traditional method, conventional method earlier, we used to have the area of rectangles, right? So for example, take this area. So what will be the area of this rectangle? This height, what will be the height? At some x, f of some x value, it will be f of x. This value will be f of x. This value will be f of x. Right? This length, this will be f of x. What will be this value? Small increment. This is delta x. So what the f of x into delta x will give you? The area of this rectangle, right? Actually, what does the force into displacement will give you? Will give you the work done. That means it is a small work done by the force f of x in that where the displacement is delta x. All right. So the force is changing here. So the magnitude of the work done will change for the same displacement, because delta x is the same, but the f of x is varying here, and f of x is at here, f of x1, it is f of x1. So slowly it is increasing and it flattens out. So f of x is changing, so the work done is adding up depending on the function, right? But here you can see you are leaving out these areas again when calculating the rectangles, areas of the rectangles. So what you do, we need to have the integration. This is where the applications of physics, application in physics comes out, right? So I have studied the integration. Now if you know how the force is varying with respect to x over the small displacement dx, so you can calculate the work done here. So there the force and displacement is given. Here see, it is smooth, very smooth, and we have to calculate this work from x initial point is this, final point of displacement is this. Between this, how much work you have done. If I have to ask you, you should ask me what is the function of the force with respect to the displacement. Okay. So as the displacement is getting more and more, the force is increasing. All right. If this function I can give you, if I tell you this is your lower limit of the displacement, this is the higher limit of the displacement, you apply the limits between them, calculate the integration of the function which I gave you, and apply the limits, at last you will get the work done between this limits. All right. So this is the area under the graph between xi and xf will give you the total work done. I hope you got this. So work done by the variable force. So if the force varies, that's what we have studied. The force varies for example, for a compressor spring. What happens? You have a spring. This is your spring. This is the block M. If I compress the spring, what happens? There will be internal force which want to push the block back in the opposite direction, right? So if I am applying some work, if I am doing some work on the spring, my force is in this direction. the displacement of the block is also in this direction, in the same direction, right? So your work done is what? Changing, because as you are pushing the spring, you can easily experience, starting it will be easy. When you keep on pushing, the force which with the spring is pushing against you will be increasing, because it is changing with the displacement, it is changing with the compression, right? That means it is changing with the value of x, your force. The more you compress, the more the force is, right? So the force is not constant there, it depends on how much you are applying force. So for such kind of variable forces, you need to use the integration. So if the force is given by f of x, then the work done by the force along the x-axis from the A, this is your lower limit, to B, this is the upper limit, is given as work is equal to square root of from A to B integral of f of x into dx. Okay, this is what it is. Let us solve one last example and we'll take leave for this session. See, find the work done on the spring when you compress it from its natural length of 1 meter to the length of from the natural length of 1 meter to the length of 0.75 meters if the spring constant is K is equal to 16 Newton per meter. All right. Now, what is the natural length of the spring? The natural length of the spring is given as how much? 1 meter. You are compressing it to the length of 0.75 meter. That means you are compressing, how much you are compressing? You are compressing 0.25, right? Previously it was 1 meter. After compression it is 0.75. How much it got compressed? 0.25, right? So he is asking how much work you have to do on it to make it compress of 0.25 meters, right? Let us see, you know the force. So the force is equal to 16x. This is the work you are doing on the spring, not the spring force. Okay, it is the force is being applied by you on the spring. That is why it is plus 16x. If the force is applied, if I am calculating the work done from the perspective of the spring, it will be minus 16x, because internal restoring force will be in the opposite direction. The spring force will be applying opposite to the displacement, so they are in the opposite directions. So that will be minus 16x, because it is in the same direction of the force. The force in this direction and the displacement is also in the same direction. F is equal to 16x. Okay, 16y, this is k. Usually you already know F is equal to kx. Okay. Now this is, you are applying the work on the, you are doing the work done by you, by external agent on the spring. Okay. We start to compress. See, we are doing the work. We start compressing the spring at its natural length 0 meters. So our reference point, this, for example, this is the reference point, this is 0. Okay. From here I kept on moving and made it compress to what? For example, up to here. So it will be some x final. Okay, this is your x initial, this is your x final. So what it will be, how much distance I need to travel? 0.25, right? From 1 meter we are compressing it to 0.75. So how much travel I have to make for the block? How much I have to compress the spring? 0.25 meters, right? So lower limit of the integral is 0 and the upper limit is 0.25, right? From 0th point I need to compress the spring by how much? 0.25 meter. So you already know this is your force, integral of f of x dx, this is your f of x dx. What is your lower limit? It starts from 0 and you need to compress up to 0.7, 0.25. That is how much you are compressing. So what is this value? I can easily write 16 x dx. What it will be? 16 into x square by 2, 8. So it will be 8x square. You need to 8x square. This is what is your lower limit? 0. What is your upper limit? 0.25. You apply the limits. So lower limit means 8. Higher limit, first you need to put higher limit, 0.25 square minus 8 into 0 square. So it comes around 0.5 something, 0.5 joules. So this is your work done. So let me see. So the 8x square, we have already derived that. Lower limit is 0, higher limit is 0.25. That turns out to be 0.5 Newton per Newton meter. Alright, this is your work done. So I hope the entire concept of integration is clear to you. So these are the mathematical tools which we employ in physics. And we also told why we are using these mathematical tools. Why we are using this calculus? Because the functions changes very rapidly, they are continuous, they are not discrete. So in such cases we use calculate, and it is a tremendous invention by Newton and Leibniz. Alright, in the next sessions we will be studying about the instantaneous velocity, average velocity and accelerations and many more interesting topics, and then we will correlate between them. So this is very interesting part of the mechanics. I hope you have understood this mathematical underpinnings of this chapter, and further sessions will come with more and more problems. Till then, thank you. Sai Ram.